We'll talk commercialization in calculus. We'll proceed in this, and we have curl in the vector field, and we will see path independence. Path independence in vector field. If I have a vector field, then what is path independence? What is path dependence? Hoop, 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 hoop. Okay, so many things are there. Okay, so consider this is a vector field. This is a vector field. If this is a vector field and this is x-axis, so this is x-axis and this is vector field. Consider this vector field belongs to force. Force has a direction. If force has a direction, it is a vector. Consider this as a force. If this is a force and this is x-axis and there is a mass, there is a weight that is kept on the x-axis. So if this is the force, then there is a mass that is kept on the x-axis. If that is true, then because of this force, how much this mass will be displaced? Okay, consider this mass gets displaced, this mass get displaced x distance. This mass get displaced x distance. Or if this is x axis, then consider this force vector has equation as xi plus yj, or xi plus x square j. These had two components. If it is a vector in xy plane, then it has a position vector. Position vector is xi plus x square j. I want to know if this is a force, then what is the work done along I vector? This is x-axis. If this is x-axis, this is a force vector whose equation is xi plus x square j. It has two components. One component is x, that is along x-axis, xi. One is x square. Whatever the x is, x square, that is the magnitude, but its direction is y-axis. Work done is force into displacement. Work done is force into displacement. If that is the case, then this force, if this is the direction of vector field, then what is the force that is along x-axis? Because I am interested in work done along x-axis, not along the anywhere else. So since I vector and j vector are orthogonal to each other, I would say if this is the force vector, then what is its component along x-axis? xi plus x square j. If that is the case, then its component along x-axis is x, x into x. If it is moving along x, if I have moved any item x distance along x-axis, x into x. Okay, but when calculus comes into the picture, then it is not straightforward multiplication. If I have a force vector that is xi plus x square j, and it has component along I axis is x, then it is as good as force vector is xi. Consider force vector is xi. X square j has no importance now. Xi. Consider altogether the force vector is xi. If it is xi, then how much is work done along x-axis? X into x. But x is variable, can you see? Force is not constant. If force is constant, that is 2. Force is 2i. If it is 2i, then if there is along x-axis, if there is displacement of x, then work done is 2 into x. But if force is x, Means as you move along x-axis, force will grow. X, force equation is xi. If that is the case, if something comes in algebra, and then what we are trying to do? If I say if force is 2 and there is a displacement along x-axis is x, then what is the work done? Force into displacement, 2 into x. Boss, 2 into x, if you say 2 into x, then it signifies two different directions for a rectangle. If you take rectangle, one side is x and another side is 2, then area of the rectangle is 2 into x. If you say 2 into x, it becomes a rectangle. If I am saying the work done is 2 into x, if work done is 2 into x, then you are actually talking about area of a rectangle whose one side is 2 and another side is x. When area comes into the picture, integral calculus comes into the picture. Then it is nothing but fx dx, where fx is 2, 2 dx is 2x. Now, if force is x, then force is x. If there is displacement of x, force is x, displacement of x, work done is not x square. Work done is x dx, x square by 2. Okay, so x square by 2. So if I have a vector field, that is a force, that is xi, and the path along which I am talking about work done is x-axis, then total work done is x dx. Fx, F, capital F, vector field is denoted in capital F. Capital F equal to F1i plus F2j plus F3k plus F4 whatever. It has orthogonal components. Consider F is F1i only, where F1 is x. If that is the case, then we are saying that consider it is, for time being, consider it is F1i and F2j. F1i is xi plus F2j is x square j. If that is the case, then if I want work done along x-axis, then F1 along F along x-axis, that is ith component, that is x dx. X component means dx as per the calculus. As per the algebra, x into x. But that is not smooth. So x dx. Okay, can I say that it is f f dot f dot I unit vector dx? X unit distance traveling we are measuring, right? If there is a x unit distance we are traveling along x axis and f is any vector, then f component along x axis first, because force and displacement has to be in same direction. If that is the case, then f dot I unit vector. So f got its component along x-axis. Now you multiply by x. So x becomes dx as per the calculus. So f, capital F vector dot unit vector I, because we are transforming f in I direction. So capital F dot unit vector I, then f becomes f1 and then into x, that is dx. So f, capital F on top of it vector sign, arrow sign, capital F dot I vector sign, capital F dot I, that is molded molded along x axis. So capital F dot I vector, F vector dot I vector dx. If I take inside the dx, then capital F dot dx vector, capital F dot dx vector, that is the work done. What is work done? If I say that I have capital F as x, if I have capital F as x, then what is the work done? then x capital F is xi. If it is xi plus x square j, then capital F dot dx vector. So capital F is xi plus x square j dot dx vector. So x vector is along x axis, then Mr. J will go out. So it becomes now x dx, that is x square by 2. Whatever we are calculating, consider this is capital F, and then this is x axis, capital F integration along x axis. This is also called line integral. You have heard that directional derivative, partial derivative along a particular axis. There is a directional integration also. It is called line integral, and it comes into picture in vector notation. If I have this vector, what is its integration along any unit vector? This. What we are trying now is this vector integration along unit vector I, x-axis. But this unit vector can be anything. If that is the case, if that is the case, then we have now, if that is the case, then we have capital F dot dr vector, means line integral of f along the r vector. Now r vector is x vector. So line integral of f along x vector. Okay. So capital F is xi plus x square j. If that is the case, then capital F dot dx vector is x dx. Then capital F, then line along which we want the integration, but line integration, if you watch closely, then it is nothing but area of rectangle that is formed by capital F components and then line, capital F vector and line vector. Then these two are orthogonal components in a way that they form a rectangular area. That is the fundamental of integral calculus. If you go with integral calculus, then you have height and width. You calculate the area. Width can be algebraic and height can be algebraic. That's where we turn him into calculus rather than simple multiplication. Okay, so simple multiplication is not the case here because height is function over x and width is function over x. If you multiply fx dx, fxx or fx dx, it becomes a kind of abstract way of calculating the area through multiplication. That is integral calculus. If that is the case, then fx dx is x square by 2. If fx integration along line vector x-axis, it results in a function algebraic equation that is gx. So fx is vector field. Its line integral along line that is r vector. Here it is x-axis. It results in another function called gx. gx gx is algebraic function where fx is xi plus x square j, and then integration along x-axis brings gx, then gx is x square by 2. Can you see one thing? That x square by 2 is gx. X square by 2 is gx. Gx is called potential function. If capital F is vector field, then gx is called potential function. Line integration of a vector field results in the potential function gx. Okay, now I have f vector. I have f vector. If I have f vector field and I am calculating the integration along x-axis, x-axis is a straight line from origin or from x1 to x2. What is the work done? Then work done is x square by 2. That is the potential function that resulted after integration. Limit is x1 to x2. Limit is x1 to x2. Now I have x1 and I have x2. No more it is a straight line. Instead of that, this is a semicircular line. Forget it. Now I am on the x-axis and x1 is this point and x2 is this point. And the way it is connected, x1 is on x-axis, x2 is on x-axis. The way they are connected is like a semicircle. If that is the case, and this is the vector field f, then what is its line integral along this curve, where from point x1 to x2, where x1 and x2 falls on x axis. Okay, if that is the case, then we did f vector dot dx, f vector dot dx, where x is x-axis line. It is not no more x-axis line. Dr, the line equation. What is the vector equation for this circle? Okay, we will go in detail. So whatever is the vector notation of this circle, whatever is the vector notation of this circle, that notation becomes the dx now, that is dr. So f vector dot dr vector. Now r vector is semicircle. If r vector is semicircle, f vector dot dr vector semicircle is the net integration, whatever it comes into the picture. We will see it. Can you see one thing? F is xi plus x square j. Okay. Now, if I consider f as xi only, consider f as xi only, not plus x square j. Consider vector field f, capital F is xi only. If it is xi, because I was doing line integration along x-axis, line integration along x, whatever the dx is, just forget the dx. Whatever we are getting x dx, that is x square by 2, it is completely the f only, doesn't dependent upon the dx can be complex also. Consider just this case. We will go more on it. So consider that it is fx dx, where dx is a path, dx is a path, x is x-axis, where capital F is xi. Okay, now it becomes x. It becomes, if I do x dot x, capital F is xi dot d x-axis, then it becomes x. That is the capital F. And then integration of capital F is x square by 2. If you see x square by 2, that is the potential function, that is the resultant, just do the derivation along x-axis. If you do derivation along x-axis, x square by 2 becomes x, that is xi. Now do derivation along y-axis, dg by dy, dg by dx and dg by dy. dg by dx, xi is the capital F, vector field F, force vector xi, xi dot dx, xi dot dx. If that is the case, then its whole integration becomes x square by 2. That is the gx. It is also called potential function. dgx by dx, dgx by dy. Okay, if there is a potential function exists, and if you differentiate with x-axis, differentiate with y-axis and make a vector, means we are trying to calculate the gradient vector for the algebraic function gx. If algebraic function gx is x square by 2, then it is xi plus 0j, xi plus 0j, xi plus 0j. If that is the case, xi plus 0j means it becomes the xi, that is the vector field itself. Means whatever the line integral we are calculating for the vector field xi, when it becomes a potential function x square by 2, and for this potential function I do the partial derivative along x-axis and y-axis, it becomes the vector field again. This proves that The line integral of the vector field along x-axis is not dependent upon the x-axis. Only vector field f comes into the picture. Vector field f, vector field f, through which we can get the gradient function. From gradient function, we can get the vector field f. This is called line independence. If I have a vector field f whose equation is xi, then xi dx, whatever dx, dr, whatever we make, the line integral is only dependent upon the f, not on the path. If that is the case, if it is only dependent on f, not on the path, then it is whatever we get the potential function. If I do partial derivative of potential function, it results back in f back again. If that is the case, then f is called line independent. F is called line independent. Okay. So that is the concept. We will do again. Line independent means if I have a vector field f and then I do the line integral along any line. If this is vector field f and I am doing line integration along x-axis, if that is the case, then this line integration results from a point x1 and point x2 on x-axis. If this vector field line integration on along x-axis results in a potential function, algebraic function gx, and if I do partial derivative of gx along x-axis and y-axis and it comes back as vector field separately, then from vector field to getting gx, I don't depend upon the path at all. Makes sense, right? If I have vector field capital F, I do the line integral along a path and it results in a potential function gx, and this potential function, if I go with partial derivative along x-axis and y-axis, it results exactly in the vector field. Means from vector field itself I can get the potential function. This dr is not required. If that is the case, then vector field is called line independent, because whatever I am getting as potential function from the line integral of vector field, this potential function, if I go with the gradient, it results back in the vector field itself, not the multiplication of vector field and the line equation. Okay, if that is the case, then vector field and its line integral, vector field's line integral full is gx, and gx is only dependent upon vector field, not on the line. If that is the case, then this vector field is called path independent. If vector field is path independent, then I can get this potential function directly from vector field. That integration is not required with dr. If that is the case, then how I can get back the gx? If vector field is xi, then xi, then x dx. Just it is same what we did, but we will prove more on it. So if vector field is x, then simply doing x dx would get the kind of would get the potential function gx. Okay, consider that vector field is xi. It is line independent. It is a kind of it is line path independent or not. It really depends upon the path. That is the question. Now path is a semicircle where one point is x1 and other point is x2, and they are on x-axis only, but it is semicircle. This is y-axis, this is x-axis. If it is semicircle, then y equal to the square root of a square minus x square. Okay, if that is the case, then the a is x2 minus x1 by 2. Consider x1 is 0. Now it will be simple. If x1 is 0 and x2 is 2a, x2 is 2a, then now it is nice. Then it is y equal to a square minus x square square root. Then what is, if that is the case, then what is the vector means this arc is represented by the what is the position vector of any circle? That is xi plus yj. Xi plus yj. If that is the case, then what is the equation? So we are saying that we are calculating f1 dot dr. So f1, consider f1 is xi. f1 is xi. f1 is xi. And then equation of the circle is xi plus yj, where y equal to square root of a square minus x square. So xi dot dr. dr r is xi plus square root of a square minus x square dy. The r is xi plus square root of a square minus x square j. Capital F vector field is xi dot dr. R is semicircle. The equation of semicircle is xi. The position vector of semicircle is xi plus square root of a square minus x square j. D outside D, dr vector. If r vector is this xi plus square root of a square minus x square j. If that is the case, then what is dr? What is dr? Then it is xi becomes dx. If xi becomes dx, so dxi plus dyj. If you do dot with xi, then it becomes x dx. Okay, same. Either you go with the line or you go with the semicircle. It is x dx. Means main thing is x1. So this is path independent. We'll talk more on it. This curl is curling, like I am talking that what is curl? We are trying to come what is a curl? What is a curl? What is rotation? Like if I am inside a river, then how I can say that if I go inside the river, it will make me rotate. So that will proceed on the curl.